All right. Good morning, good evening, and good afternoon, everyone. Thank you for tuning in. I think folks will trickle in as we're doing this. I think we've got over 100 folks, and we just went through a list. We've got folks from all over the world. So thank you for making the different time zones from 9 a.m. to 9 p.m. And today I'm very excited and thrilled to share with you some recent work and the very first public tutorial for quantum device design of superconducting quantum processors with Qiskit Metal, which we just launched last week. Or the subtitle of this talk is How to Make Your Own Quantum Computer or Your Own Quantum Processor. I think this is the first open source quantum hardware project that does the full thing to my knowledge. So really thrilled to be here today. I'm Zlatko Minev, PI and tech lead of this project, and it's maybe a good place to begin with what is Qiskit Metal? Let's begin with a little bit about that. Well, designing quantum devices is the bedrock of the quantum ecosystem, but as you know, it's a difficult multi-step process that connects traditionally disparate worlds, from engineering to software to physics. But the hope and vision for Qiskit Metal is to automate and streamline this process. And our vision is to develop a community-driven, universal platform capable of orchestrating quantum chip development from concept to fabrication in a simple and open framework. And I think the 100+ people we have here today on the call is hopefully a first good step in that direction. So we would love to accelerate and to lower the barrier to innovation of quantum devices to put fuel in the fire of the furnace of innovation. And today is the first open source public tutorial.
Hello.
I'll be giving the tutorial, and next week we'll have Dr. Thomas McConkey, or Thomas, give a live code demo of how do you actually code this thing up and do hands-on live demo of how to use metal to design a small-scale quantum chip. But today I'll focus on the bigger, broader picture, and the subsequent tutorials will cover more in-depth different approaches, methods, and so forth. Now, before I begin, I really want to just pause for a second and appreciate everybody who's helped make this possible from the team here on Qiskit Metal. I think I started this project about 2 years ago, and it's since I've had the pleasure and privilege to work with all these people who've joined. So I wanted to send a huge thank you to the whole Qiskit Metal team. I think most of them are here on the call, and you can interact with them in the Slack channel. And a lot of the work you'll see has been tremendously done by these folks. So if you're feeling a little bit lost and you've just joined and you're not sure where things are, where do you go? Well, the homepage, qiskit.org/metal, is a great place to start. Then there's the documentation. I think actually we've done a pretty awesome job with the documentation, and there's some more tutorials coming there soon. The actual source code, it's fully open source. You can download it, you can make issues, you can make pull requests, push back code back into it, is located on GitHub. And there's pretty extensive directions on how to install that. And then finally, if you would like to ask questions, discuss with us, the Slack channel, there are instructions on these pages how to get on it, is a great place to discuss and talk. So this is what the orientation looks like. There's the main web page. If you click this video here, there's a very nice introductory video to Metal. It's about 2 minutes. Today you're going to get the 1-hour version of that. And we also have, if you'd like to read more about what is Qiskit Metal and how to use it, we could go then to this blog. And I think, Marco, if we can mute the noise, that would be great. Thank you.
Need to actually stop, but yes.
Okay. So if you'd, again, like to know even more about the bigger picture and sort of where metal fits, there was a few really nice press releases that came out in the last week or so. So I can, direct you to take a look at that. So where are we today and where are we going to be headed? Welcome to the tutorials. Today is the very first tutorial. We're building these tutorials off of the last 6 months, during which we had a small early access cohort. Some of these folks are probably on this call today, where we worked with folks to kind of build up an early access alpha version of Qiskit Metal for quantum device design, going through how to install it, how to design a transmon qubit, how to create a 4-qubit small chip, how to export it to something that you can create in the lab, how to analyze it and simulate it using various approaches. So we'll do some of that in these tutorials, but today I'll just focus on the bigger picture. So about today. So who's here? Feel free to type in the chat whether you're a grad student, a professor, an engineer, a scientist, a researcher, a developer, a software engineer, just a newcomer. Please let me know. I'd love to know. So there's a little Slack channel that will tell you that. Yeah, so please let us know who's here. I see physics grad student, engineer, and scientist, and I figure we have folks that are both newcomers completely to quantum in the field who've maybe heard about what metal is and are interested to hear more. We have probably a lot of grad students designing quantum devices and superconducting qubit labs. And I'm sure I know we also have a number of experts in the field who are on this call and who've been using Qiskit metal to design quantum devices and to actually fabricate them, measure them. You may even put them in the cloud. So it's a very awesome and very diverse audience in terms of background. And as you know, and you see from the chat, we have experimentalists, we have theorists, and we have software developers here and engineers. So this is a wide array of different disparate typically backgrounds, but that's what it takes to build something no one's ever done before, to build a quantum computer, to innovate quantum devices. You have to bridge across different disciplines a little bit. And so Qiskit Metal hopes to make that easier for people who come from an engineering background or from a physics background, so they don't have to reinvent the wheel, but sort of leverage tools as much as possible. Of course, that presents a huge challenge to me as your presenter today on how to get everybody on the same page. So to do that, I'll start with a very broad overview of quantum device design and quantum processors, and then I'll slowly get more and more technical. And then in the next series, we'll have a kind of hands-on coding demo. So some things will be more broad, some will be more technical. I'll try to do a little bit of each. And the process for today is pretty much oriented like this. We have the beginning, which is what exactly does it take to design a quantum processor? And then the second part is, now how do we make that easy? How do we make that click of a button as much as possible with Qiskit Metal? Now, with that, nice phrasing, I'll just give a caution mark. And the caution mark is that Qiskit Metal is an early stage source code. It's open source. We've just started. This is like literally day one, technically. And it's early in its days, so there's a lot of room to grow. We've already designed and made and measured several devices with it, so it can do a lot. But keep in mind, it will change. The code will evolve. It will grow. There will be bugs. It's an early prototype. But we're excited about the vision, and so excited to have you join the path. So how do we design quantum chips, and where does Qiskit Metal fit into all this? Allow me to back up quite far for just a minute and start with something quite near dear and familiar to all of you here, and that is your laptop, which is probably where you're logging into today. Now, you can log in from your laptop into a lab or cloud facility these days, such as this IBM one here, which itself houses a cryogenic environment for a superconducting quantum processor, and you can run quantum experiments and so forth on these. And as you know, this golden chandelier is mostly just input-output cabling for the thing that's the beating heart of the actual quantum machine, which is the chip, the quantum processor. That's really the only quantum thing in this whole picture. In all three of these pictures, the only quantum thing is this last picture here. So that's really the most important piece in a sense that underpins the entire quantum ecosystem, because it doesn't matter how good your quantum software is if the quantum hardware can't support it. So how do we innovate? How do we make rapid prototyping of quantum devices in a flexible, extensible, and diverse way? So let's take that one level down, and this is bridging into a whole new level of what Qiskit has touched. Until now, there hasn't been, if you want, anything at this level of the stack, and this sort of completes the stack. So how do we design a quantum processor? Well, at the bottom level, if you want, there's the physical layout. It's some pieces of metal on a chip, some pieces of geometry, some polygons. But the next thing you might ask is, well, what do these mean? And all of these quantum devices are, to first order, just microwave resonators, just like your microwave oven in your kitchen. They have a resonance frequency. They have microwaves that can oscillate in them, except that they're at the single photon level and they're quantum things. So at a first pass, the way we analyze and design quantum processors is very much like classical conventional processors. So if you're an electrical engineer or you've done classical chips, this will look very familiar. You'll be like, oh, I know this. The first step is to do some microwave simulations, whether it's scattering matrices or eigenmode or just electrical spice simulations. And that's so far so good. Now, the next part is when quantum departs from classical, and that's that these resonators aren't just nonlinear, but they're also quantum. And so we have to have techniques, we have to have approaches that can bridge the classical to quantum gap and take you into the realm of quantum, where we now talk about wave functions, we talk about Hamiltonians, we talk about energy levels that are discrete. The energy can't be anything you want. And there are quantum interactions between these that allow you to do 2-qubit gates and things like that. So how do you go between these techniques? Well, Qiskit Metal will have and actually has already a number of these so-called quantization approaches built in and largely automated. And so the final step is from that Hamiltonian, which is where now theory also comes in, to extract and distill what is really the logical qubit space. What does my qubit look like? What is my transmonad harmonicity like, or so on. Now, I wish it was that simple. Unfortunately, if you pick some geometry and you go through this multi-step process, you can't just suddenly get what you want. Rather, you get something, and that something doesn't correspond to what you want. So what you have to do is now iterate. You have to go back and say, okay, how do I now tweak my physical layout in order to reach the desired quantum device that I want? And so you have to do this over and over and over again. So when I was in grad school, I think I spent 3 to 6 months designing a device to do this, and it would take it was a slow, laborious, long process. And we'd like to make that simple. So I think Thomas will show you next time how to do this basically in an hour roughly, and maybe with more tuning you can do it in. We did a hackathon recently, so folks were able to design their full quantum chip and tune it quite well within 2 days. So we're on a path where you can start to do some of these things a lot better. So in terms of the big picture, what's the takeaway here? Takeaway is we have some physical processor that looks like this. It's classical, and we also want to understand its quantum properties. And Metal wants to make this as easy as possible and build in best practices and so forth. So what does one of these devices look like? If you zoomed into it, it looks kind of like this. Yours might look different if you have an XMON lab or something like that, or flex tunable lab. It doesn't matter. It's just geometry. It has metals, dielectrics, so-called readout resonators, qubits, Josephson tunnel junctions. So what do you need to design? Well, you need to design the geometry, topology, the frequencies of all the qubits, the different couplings between them, local and non-local, the many-body Hamiltonian, the input-output coupling, the dissipation, Purcell, and spurious modes, loss budget. Basically, there's a bunch of stuff. There's quite a lot that one needs to worry about. So we'd love to have this approach can handle all of that at once. So that's what Qiskit is in a big picture about. Now, how does it work and how does it make life a little bit easier? Let's do this by an example, by laying out, analyzing, and optimizing your first 4-qubit chip. So where do you start? So I would start by going to github.com, Qiskit Metal, download the code, scroll down, and you can follow this very nice YouTube instructions. I think Marco made this video that has a step-by-step guide as to how to set up the actual code. And there's also a very nice documentation, and you just play it. It's on YouTube. Now, once you've done that, or if rather you're a software developer and you'd like to get started, you can go to the issues. You can click label and go down to good first issues, and that might give you a sense of what are some interesting first projects to dig your teeth into. That should be pretty easy to tackle, hopefully. But let's move forward and actually apply this. So let's start with a guest layout. And to do that, we'd like to create a transmon qubit. That's the bread and butter of superconducting quantum circuits. So from Qiskit Metal, there's a library of predefined quantum components. You can make your own if you don't see the one you want. And you can select the, let's say, the transmon pocket, give it a name and give it some custom options. And then you can pick up the GUI if you want to actually see what this will look like. Now, how do you know what this library is and what it contains? Maybe the easiest way is to go to the documentation on qiskit.org documentation. And here there's a number of very nice examples of how, if you want to make a crossmon or an xmon, if you want to make a single floating transmon, a concentric transmon, there's a number of different sort of built-in components, CPW, coplanar waveguide meanders, tunable couplers, direct couplers between two qubits, resonant bus couplers between two qubits, if you want to have launch pads, readout lines, and down the line, we're also hoping we will add 3D structures as well as these planar structures. So let's say we select our favorite transmon qubit, which looks something like this. Okay, you can create it by clicking that little link, and that will take you to a page which walks you through a short mini tutorial on how to create that transmon qubit. And you import it from the library of qubits, and then you can give it some options, where it's located, what is its rotation, how do you call it, all this stuff. So it's quite customizable. Now that's if you want to use the source code. You can, alternatively, if you don't like to code, but you prefer a nice visual GUI interface, you can use the Qiskit Metal GUI, and here's what the outcome of running that particular experiment looks like. Here's the transmon pocket defined inside of or plotted rather, in the metal GUI. And on the left here, we have a number of its properties that you can adjust, in real time, because we'd like to have that tight integration feedback loop. So you can vary all its properties and see how it changes. Hopefully the movie's playing through the bandwidth here. But you can change all of these properties in real time and change the geometry. Now, you can do that not only, of course, with that transmon, you can do it with different kinds of geometries, and you can define your own, such as this xmon qubit here, and there's a particular coupling. You can add a second coupler and so forth. This is just to give you an idea of how that looks like. And all of these look a bit like P cells, in that parametrized cells, in that you can change all the properties, but they also have a number of other features that allow for simulation, which we'll get to in a minute. So how do you now take that building block that you've got nicely well defined, and how do you scale that up? How do you make something more interesting? Right, one qubit is nice, but let's just start with the classical layout and just make it easy. Let's take that and repeat it 4 times in 4 different places. So all I've done is taken that same qubit of the same class, which is called Q1, and I've placed it in 4 different locations with a little bit of code in the background. And then I've used a different component from the library called a coplanar waveguide, which I can tell very nicely to just connect 2 parts. So for instance, if I want to connect qubit 3, pin A, to qubit 4, pin B, you can just tell the coplanar waveguide to have a length of so-and-so and define its start point at Q3A and Q4B. So if you move any of those, then that will give you, let's decline that, that will give you an auto-routed guide there, and you can vary that. So in a following tutorial, we'll explain more about the very nice features and functionality of those. Now, if you want to have, so what do we have so far? So we have 4 quant qubits, which are each of these little transmons connected by coplanar waveguides. So those will give us some interactions between them. But we also need a way to get information in and out of the chip. So to do that, we can go back to the library of quantum components and pick out the input-output couplers, which we've selected here. And again, use the routing algorithms to have several direct charge lines. And you can really go crazy with This is just to show you that built in some of the features we've started to build in are these sort of hybrid auto routing A-star path algorithms, and you can go pretty crazy with what you can do. But maybe let's move into the next step, which is now we have some processor laid out. What kind of processor is it? How good is it? How well does it do? What are its quantum properties? What is its Hamiltonian? What is its dissipation? And this is where we need to start to bridge the classical to the quantum and go into the world of cats and Hamiltonians and block vectors and so on. So how do we bridge this gap? Okay, so the next slide is a bit of a more technical slide for the more physics folks in the audience, but let me give you the broad picture and overview. There isn't one technique to rule them all. There's rather a landscape of different scientific work that treats this problem at different levels of complexity, going from sort of the simplest lump models, which operate in a quasi-static regime, meaning sort of low frequency approximations. And then there are complicated full wave models, or rather not complicated, but models that capture more of the complexity of the device based on either the impedance or the energy dissipation ratio, which can tell you even more about the quantum device and can capture all of its glory in terms of Maxwell's equations and really tell you a lot about the dissipation and the Hamiltonian. And the idea is that in the design process, you can't just pick any one of these techniques. Typically, you have to usually use different techniques at the different stages of your design, or maybe you have reasons to use one or the other. So we have already built in the energy participation ratio quite fully. We have the lumped built in, quite automated, and also we've now have some of the impedance approach built in as well. So in the capacitive approach, which I'll give you a nicer overview in just a minute, you can start with a physical design, export it to some quasi-static simulator, get a matrix and get out properties. Then there's the eigenmode approach, which I'll also talk about. These are pictures from Qiskit model and what you can actually do with it. And then there's also the impedance, admittance, and scattering matrix simulations that one can leverage existing commercial tools. These aren't things that we want to replicate and reinvent the wheel. People know how to do impedance and eigenmode simulations incredibly well. We're going to use those existing backends. We call them renderers, the existing software, and we're going to interface with it very tightly in an automated way so that we can extract what we need for the quantum part of the analysis. So here's a demonstration of how one can go about and start to do that. We can start with this picture of our 4-qubit quantum device. And here's a video where we've now, for this particular thing, we've chosen ANSYS HFSS. The idea is that we set this up in a way where one could do this with, in principle, COMSOL, maybe Keysight's ADS and other softwares. Those renderers are things that we'd love to work with somebody to write. But for the moment, we focused on this one since this is the one we tend to use. So let me play that again and explain what's happening. So we have Qiskit Metal here in the background. And this is in the foreground, we have a simulation software. And now we can take the chip from Metal, render it into HFSS here, run a simulation from Qiskit Metal, which can tell you about, in this case, what the qubit electric field looks like and its coupling to this readout resonator. And we can extract in return the frequencies, the eigenfields, meshing and all this stuff, and plot and automate. And this happens in real time. So that's kind of the bigger picture idea. Let me illustrate a little bit more on the capacitive analysis method. So in Metal, you have some device layout, which maybe looks something like this. And you'd like to know the Hamiltonians of the qubit, the readout resonator over here, this bus coupling resonator, this other resonator. You'd like to know what those are from the device layout. You'd like to have that tight integration. So with Qiskit Metal, Thomas will show the details of how to do this next time, you can automatically export this into a simulation backend, such as ANSYS Q3D here, which creates kind of a nice 3D geometry model. it identifies the signal nets, or basically metallic islands. Each of these metallic islands represents a piece of metal that can have a different voltage. You can then run a simulation which looks at, which creates some meshing and then looks at what the capacitance between any two pieces of metal in the simulation are. And again, automated with metal, you can then extract out the capacitance matrix of this circuit. Okay, this is sort of the simplest thing you can do. Now, from that capacitance matrix and knowing the circuit, you can create, metal does this for you, but I'll just describe what it does. Metal then creates for you this sort of graph network of the actual device model, and from that creates the Hamiltonians of your transmon qubit, corresponding exactly to the physical layout. So you have this very tight connection. You're not guessing the capacitance values here. And it tells you the dressed, loaded resonator line parameters. It also finds the interaction Hamiltonians between the qubit and the readout, the qubit and the other resonator, the readout and the readout. It does all of these different parts together. And so if you want to know the actual physics and you're really deep into the theory or the weeds of this, I invite you to take a look at this preprint that we just put out 2 weeks ago on the archive that talks about this particular quantization method and some of its very nice features. I'd also like to then say, what's the next step? Once you do extract the Hamiltonian, you can then find its wave functions, you can find its eigenparameters, you can plot the wave functions of the transmon qubit as a function of the energy level. And I'd also like to acknowledge here Chris Warren, whose face I think you see several times in this talk, who contributed. He was a very nice Cooper Bear box class. Chris is at Chalmers, and he's been one of the early adopters of metal and has really done some awesome contributions back to the source code. So encourage everyone to give him a thumbs up and to do that yourself down the line as well. And so this is perhaps the simplest way you could treat things, is with this capacitive approach where you extract parameters. Now, if you want a more correct approach, in a sense, even though the capacitive can work really well if you have planar structures, but if you have three-dimensional 3D structures, cavities, or you want to really get at the details of things and get things very precisely, then you can apply the eigenmode approach, which doesn't take this approximation that things are capacitors or inductors. It just simulates Maxwell's equations to their full glory and beauty. And so for details on the physics of that, take a look at this paper. Here, I'll just give you the big picture. So the big picture is you take a part of your chip that you're interested in, like these two transmon qubits, say connected by a coplanar bus. You render them into, Metal renders them into, at your discretion, into a simulation backend, such as HFSS. Metal automatically puts in the boundaries, what are metals, electrics, dielectrics, etc. It then builds in best practices for meshing operations, for putting in junction lines, etc., for how you define the coplanar waveguides in an efficient way. It puts in native curves. It can do all of this automatically for you. And you have quite a bit of flexibility, because what you're doing now is you don't want to analyze the entire chip at once, because that's just way too much at once. So usually you simulate parts of the quantum chip. And to do that, you have to be careful about how you break up the quantum chip. So we've been very careful, and Dennis did here a lot of work on when you break up the model and render it into an analysis, whether things are open or short or something else, you can really tailor very carefully and neatly each of these properties here. So we've seen much better performance results with simulation when we've rendered things with metal rather than importing straight from something like a GDS file, because we do these native curves for the meshing and so forth. So we've seen some good performance with the best practices we've tried to build in, like with smaller RAM and so on. Once you do that simulation, you can use one of these quantization approaches to extract its Hamiltonian, to diagonalize that Hamiltonian to extract its properties. And again, that's something that is just a function you call in metal. Thomas will get into the details of how that works, but here's an example. And from that, you can create, Metal creates these automated reports for you. So here's a report of the qubit frequency and the qubit anchromonicity as a function of the simulation pass number. And you can see that you can monitor the convergence of how well the qubit frequency has converged to its value of 5 gigahertz and its anchromonicity of 330 megahertz here. So you can really be certain in your simulation, because you don't want to confuse yourself, because simulations always give you a number, but is it a good number? You can use plots like this to get an idea of that, as well as things like the coupling between two devices or their linear G. So a lot of these things are built or being built in Metal currently. Now, excuse me, once you have finalized your design, the next step is to say, how do I now take that and make it into a fabrication facility, for instance? So you can export your design after you have finalized it by clicking the GDS export. And I know that went really fast, so I'm going to play that movie again, but I guess that's maybe the point, that it's easy. So you click up here, the GDS renderer. The GDS renderer has a bunch of options as to what you want to export, what are the tolerances, do you want that, I guess we'll have to add, is it positive or negative mask, all these kinds of details. And so Pretty and folks here have done some great work on creating this very nice render that just takes what you see in Metal, exports it into a GDS. It also puts in your sort of custom Josephson junction parameters. You can't quite see the junctions here, but they're in there, into the layout as well. Good. So maybe that went a little fast, but you're done. Basically, you've created your quantum chip at this point by following those analysis and optimization points a couple of times. So then we can ask, this is all nice, at least in theory it works, but how well does it actually work in practice? And so that's what I'd like to show you next. These are results from this recent paper we published with a couple of colleagues here. So this is my personal notebook working in Qiskit Metal, and I've simulated, I don't know, 10 different qubits or something here, and they're qubit frequencies and harmonicities, readout frequencies. These are all part of a larger chip, and their readout dispersive shifts called the chi shifts. The qubits have different number of buses, and anyway, there's a bunch of properties. When you take this all in, you ask, how well does it work? Now here's some data on measured versus predicted. So here we've measured the dispersive shift between the qubit and the device versus the qubit readout dispersive shift. Here we've said what is the prediction between the qubit and readout dispersive shift. This is using an old version of the analysis code for lumped methods. We've now brought that down from 20 to 10% in the new paper, but this is to give you an idea. So if you use the lump, you get a pretty good, reasonable agreement. But if you use the energy participation ratio, we found a 4% agreement between theory and experiment when you account for things like the junction inductance. And you can also add in and compare against the impedance approach as well. And that sort of gives a 7% agreement. So basically it works really well. That's sort of the bottom line here. If you do things right and use the best practices and you use the analysis correctly, you can get really good agreement, at least on our types of devices. Now you might ask, what other kinds of devices can I use? So here's an example of I think this might have been Thomas or someone creating a different kind of qubit device, not the one I showed you earlier, but creating a hanger resonator. So these are 4 qubits connected to readout coplanar waveguide resonators with some launchers, and they can all hang off of a feed line. And you can also take that and simulate it and so on. Next time Thomas will talk, I'm not sure he'll present, maybe he will, but he can talk about much more complicated chips and things like wire bonds and XMONs and direct couplers. And this is something created with Metal. I think it was mostly just a fun design we played with. but you can go a little more complicated. So hopefully at this point, I've illustrated to you some of the core ideas and vision of Qiskit Metal. The aim of Qiskit Metal is really to be an end-to-end automation and analysis tool between the Hamiltonian and the very physical layout and device of it. We'd like to have that very tight feedback loop. We also want it to be very flexible and extensible. So it's both an API Python code, but it's also a visual interface GUI. And we don't want to specialize it to transmons or Fluxonia or 0 pi qubits only. It could be any of those and newer ones. We want it to be lightweight and interoperable. So we leverage existing analysis tools as much as possible, and Metal integrates and pulls their power and helps you do that in a way that is experimentally tested and verified. So what we've put in and what we are putting in, we use ourselves and other people use it. So it's really experimentally tested. We've seen great agreement if you do things the right way with Metal. It also gives our vision for Metal is to also have a library of shared common components that folks from the community can hopefully come around together, and we can build this in a unified way, because quantum is hard and designing devices should be the easy part. Innovating devices should be the hard part, but we'd like to make that as easy as possible with Qiskit Metal. And it's also a good way for folks that are new to the quantum field to come in and bring their skills and help contribute to the challenges we have. And we built in sort of the best cutting edge resources and analysis techniques, some of which were published just 2 weeks ago. So this is really quite hot off the press here. Now, you might ask, this is all very nice. Can you tell us a little bit about how you've used this, who has used this, and what devices have been made with Qiskit Metal? Well, I'll start by bringing up what I believe is the world's first quantum hardware hackathon, to my knowledge. And this was, I don't know how, but somehow we got famous in Korea. And we got invited to this hackathon, which we were quite surprised about, but also very grateful for. We decided, sure, why not? Let's do it. So we had 3 teams of 4 to 6 students and folks in Korea, some of which had zero experience with, well, nobody on those teams had ever seen Qiskit Metal. I think very few of those folks were really quantum experts. But they took on this hackathon project to design a 2-qubit quantum processor. This is the actual project, and use Qiskit Metal in just 2 days, having not installed it before, to design this 2-qubit processor with these particular qubit frequencies and harmonicities, these couplings, to specification essentially. And so here's a couple of screenshots from the hackathon. I'm sort of very pleased to say that that folks were able to my shocking both pleasure and demise, create a 2-qubit quantum chip and do simulations and tune it in those 2 days with Metal, having not used it before. I say pleasure and demise because it used to take me sort of like 3 to 6 months to make a device back in grad school, and these folks in Korea were able to do it in like 2 days. So, it makes me wonder, what did I do with my life for those 6 months when it takes 2 months now? But I'm also really happy that we can help bring that down so much. And of course, Metal is early in its days, but we're quite thrilled. So big kudos also to the team. Thank you, Mihat. I do see your reaction or emoji here, so feel free to use those. So that was a really sort of unexpected and really fun and awesome experience. We're hoping to have another hackathon. So if you're interested, give the thumbs up here on the reactions panel. Yes, perfect. Thank you. That's awesome to see. Wow, that is a lot of thumbs up. So I guess we definitely have to do another hackathon. They're great, by the way, for learning how to do things. Wow, that is a lot of thumbs up. Awesome. All right, I think that's a big kudos. We're definitely doing a hackathon. Now, what about big devices? Well, here is actually, this is the exact device that we've made. It's not a fake. This is actually the device that we made for IBM Tokyo testbed. It's called Tsuro. It's a 5-qubit device that Thomas, John Blair, and the team here designed and made that this is going to Tokyo actually, and so that's being fabbed. It's a 5-qubit device. Here's the 4 qubits connected by buses. There's an extra 5th qubit. There's some other structures on the chip. And we've recently made and fabbed this, and we'll have experimental results soon. So we designed this with the help of Qiskit Metal. Now, we also had this amazing experience, and I'm actually quite surprised this happened, to be honest. We wanted this to happen, but I didn't think it would happen. So we had a short early access program, which lasted from something like November till March, which is, Christmas, March meeting. And despite that, Chris Warren and team here at Chalmers University were able to, learn how to use metal and, help design their standard, redesign their standard, I guess, 8-qubit quantum processor, which kind of looks like this quantum chip that they make, simulate it and render it with metal. Here's a simulation. This is the metal GUI on the left. This is a simulation of one of the qubits inside of ANSYS HFSS, and I think that's its electric field radiation profile. There's the Josephson junction simulated there. So anyway, so Chris, Amor, and Jonas's group were able to make this chip, help design it with metal, make it, cool it down. And just last week, Chris sent us some experimental data. Yes, thank you. Yes, that does deserve a clap. So thank you for that reaction. So here is a spectroscopy, two-tone spectroscopy curve of the 8 different readout resonators. These are each of these lines dips here corresponds to a qubit. This is experimental data. On the right-hand side, we've zoomed into one of the qubits, and you can see its qubit frequency transition line here, 0, 1. And here is the 0, 2 over 2. This is the anharmonicity of the qubit. Our qubits are in 2 states. They have many more states. That's why they're called transmon qubits. So this is really an awesome kudos to Chris and folks for doing this so quickly. And if you are working or making or have made chips with metal or plan to make them, we'd love to see those results in Slack. And it means a lot to the team and us, I think. So thank you for sharing those, and please do share that. So how do we install Qiskit? I think I just saw a question about that. How do we learn about Qiskit Metal? How do we use it? How do we just, let's say I'm not a physicist, I don't need to know the physics, but how do I just make the most of this? Or how do I learn about this whole, the code or just the big picture stuff? And how do we build this together? So that's the final part of my slides here. Well, I think one of the great places to begin is to discuss in Slack. I'll try to get as many of these questions as I can in the rest of this, but a great place where you can follow up, and we've been super active. So thank you everyone else. Thank you to everyone on the team for replying to all these messages. You can see, 6 replies, 4 replies. Slack channel is a great place to do that. I think Grace is probably the first one to always, like your thing. So big kudos to Grace for that. Anyway, the next place where you can go is the documentation. The team's been really awesome and great about being quite exhaustive, and we have a lot of sections on how do I get started. We even have a roadmap, what's being requested, and on there, if you have requests, put them in the Slack, put them in here. There's a contributor guide, there's the tutorials that's going to expand a lot, there's the example library, etc. Do note, though, I will emphasize this again, all of this is changing, and this is going to keep changing. Metal is growing, and it's still early in its days, so it does a lot, but it's a prototype. So there'll be bugs, and we'd love to know about them. Now, the next place you can also go, especially if you like to know a little bit more about general physics or just getting into this, is to have you check out this page, which leads you to a series of lectures. These are summer school lectures. We had, I think I gave a series of 6 summer school lectures on an introduction to superconducting quantum circuits. So if some of this is new or some of this is something you like to understand or learn better about, whether you're a physicist or just getting into this, I can recommend you to this 6 lectures. There's also notes, and there's a lab that goes with it. We had, I think, 4,000 students at that particular summer school, so I don't know, the largest to my knowledge. It was really fun. If you really want to go deeper into this whole community and stay tuned, we also host the Friday Quantum Information Science Seminar with Olivia and myself here. So we have a lot of the sort of foremost experts in the world talking about the latest in research. So take a look at that if you're interested in knowing more about the field. So I think with that, I'm coming to my last slide here, and we'll have 10-ish minutes for questions, which is that Qiskit Metal is at its core a community project. I think the idea here is to do this together, to build this together, to making quantum devices more open sourced and easier. And I think that's important for fueling the fire of innovation, because what we have to do is keep up with expectations, and being able to innovate rapidly, prototype quicker is, I think, quite key. So we're very committed to both the open source, and we're very committed to pushing the science along with it, as you've seen in some of the publications in archive papers, as well as the education. This is not a problem that is only handled by physicists. It's not a problem that's only handled by engineers, and it's not a problem that's only handled by software developers. We need all of these folks to kind of learn and work, and we're hoping Metal can be a good entry point for that. So check out the textbook, check out the lectures, documentation, and so forth. And so with that, I'd like to thank you for your attention. I think stay tuned for the questions. We'll take those now. But that concludes my talk. And then next week, Thomas will actually show you how to actually do everything I sort of glanced over today, and do a hands-on demonstration. So thank you for the claps. And I think with that, maybe Marco, do you want to help triage questions here?
Yeah, so first of all, thank you for all the questions. We have been trying to answer them. All the entire team has been answering question one after another. First, I want to remove the audio block. I want to allow people to unmute themselves, because we might have missed some of the questions, and I would like you to open up your microphone and ask it. I think the one that we didn't answer, just the most recent, can we apply inelastic scattering in the simulations?
I think, yeah, that's maybe a little off topic.
Yeah, I think it might be off topic a little.
I see a question from Renato that just came up. Could you read that one? Or I see questions piling in now.
You'll get the chance. You guys cannot unmute yourself. If you can, just unmute yourself and ask the question.
I hear somebody.
Okay, this Renato's question is the Hamiltonian tunable once the chip is done?
Oh, good question. Yeah, so let me back up to that. That's a great question. So how do you tune the Hamiltonian and so on? Well, if I go back to this picture, if you have some particular physical layout, that corresponds to a Hamiltonian. Now, what that Hamiltonian is sort of fixed by the device. So once we go through this analysis approach through the electromagnetic, the quantum part, and reduce it onto the parameters we want and extract those, that's it. If you don't change the device, that's it. That's your Hamiltonian. So that's why Metals has tried, that's why we have the layout integrated with the simulation and analysis so tightly. They're not separated, they're together, so that we can do this tight, closed feedback iterative search process where we iterate over and over again through this in a sort of rapid way, in order to be able to tailor the design subject to the constraints of what we want. So we can see that, we didn't get what we want, let's just adjust that, let's run, click a button, run my eigenmode analysis, run my capacitive analysis again, these analyses here, and get out the new Hamiltonian. So unless you've fabricated your device, you're good. You can change it.
I have two questions. Sorry to interrupt. Are there any textbooks that you'd recommend in terms of understanding transmods and Josephine junctions a little better?
That's a great question. Honestly, there isn't yet one great textbook that I know of to totally cover that. The best things that I know of that we're also building up as we speak are probably the Qiskit textbook, and I think we plan to, with actually the help of folks here, if folks are interested in turning some of what you've seen today and in the following tutorials into a textbook, we're going to be writing an open source textbook. So if you'd like to be a co-author on that, with significant contributions, then reach out. So I would say that the summer school lectures are probably at least to my knowledge, maybe the easiest entry point. I mean, I gave them, so maybe I'm very biased, obviously, but to my knowledge, that's a good entry point where it really talks about junctions and so on. The Qiskit textbook is a good place. There's Steve Gervin's Lezouche notes. That's another good entry point. And I don't know of a dedicated textbook yet on that, but maybe Slack me and I'll think of more references. I do have a list, by the way, of number of review articles from Will Oliver that came out recently, and Will Oliver and team, Alexander Blay and team had also a very good review article. But those are more academic and level, so hopefully that helps a bit. Not quite textbook.
Zlatko, there are two questions from the chat I'd like to point out. One was they were asking, what's the materials database like? Like what materials are already included? One question. And the other question is a combination of several, which is asking about how stable is the interface to other simulation programs like COMSOL or CST?
Great. Thank you. That's a good question. So materials, you can specify any material you want in the properties of the transmon qubit. That material has to exist. You have to define it, or we can add it to the simulator. So for instance, here, I think this chip is sapphire. You could choose it to be silicon. You can define your custom material as well. So it's quite versatile in that way. I think the materials is something that's still being developed, so it works, but there's probably some more room for things to grow. So if you have more detailed questions, maybe ask us on the Slack channel. The second question was on, remind me the second question.
Interfacing with other simulation programs like COMSOL or CST. One person was asking if you already have interfaces to those particular brands, and the other question was asking how stable is it?
Oh, great question. Yeah, so we have, currently we have several renders. We have the matplotlib one, which just renders the thing and shows you a nice view. There's the GDS one, so if you need to export to GDS, and you can take a GDS, I guess, and import it. For the real-time analysis and simulation, we have a very well-developed, very stable, very robust, pretty robust ANSYS interface. It's a real-time interface, so you're not saving a file. You're actually controlling in real time the ANSYS software as if you're clicking it essentially, but it's an API thing, so it just happens in the background, and that's basically very powerful. It's quite stable, I think. Occasionally you might see some bugs and issues, so if you do, let us know. But if you set things up right, it's we've been using it a lot and we'll be using it, so that's going to be quite well supported. For other things like CST, like Qiskit, like other simulation tools, I think those are things that we're hoping that people who do use those can help us develop. We can help you, co-develop them. But I think that would be great to do as a community together. So if you have interest, reach out.
The question is how many other devices or technology we are thinking to support, such as optical systems and 3D structure, etc.
Oh, yeah, that's a great question. I think for the immediate moment, there's a lot of work to do for us just on superconducting qubits. So that's our immediate focus. That's what we're focused on. I think long term, I was talking with my buddy who's doing ion trap design over the weekend, and there's some similarities in terms of simulations that you might do as well. Simulations are similar. You need to do electromagnetic simulations, so we'll explore and see whether it makes sense or whether there's a community that's interested in that. So I think if there's a lot of interest, that's something we can help grow and help expand over time as well. The immediate focus right now is superconducting quantum devices. But at the end of the day, if your device looks like polygons on a chip, you can probably design it with this, because at the end of the day, this is just a bunch of polygons, and they have some extra properties as to are they metal, material, and so on, and then you can export them, do an EM simulation or do a quantum simulation, and you have a very nice sort of Python API framework around it.
Zlatko, there is a question that I've got privately. It's can we apply inelastic scattering in the material chosen, especially carbon quantum dots?
Yeah, thanks, Priti. So I guess quantum dots are probably something that would be quite potentially to a degree similar in terms of the physical layout. So quantum dots are they also operate on a chip, and they're more typically electrostatic based. So you can define a number of little wires, gates that can confine electrons in a very small space, and you can confine them to in such a way that you can have only one electron or no electron, things like that. And also there's a lot of simulations there. So I think you could draw that chip and do the regular EM simulation. Inelastic scattering and those quantum dots, I think, is something that there's some code written out there. I think I don't know if it's open source, but I know some people have worked on it. I know that it's challenging to do because so much of the inelastic scattering depends on the material properties of the actual device and chip, and those are hard to control experimentally. So the predictions are trickier to make. If there's people who are interested in helping write like a plugin to Metal to do that, I think we'd be sort of more than happy to welcome that. But otherwise, it's probably a bit quite technical and specialized.
Another question I can say that comes up a lot is how do we connect Qiskit Metal to the rest of Qiskit?
Oh, great question. Yes. So Qiskit Metal really opens completely new direction for Qiskit. I mean, Qiskit so far is Qiskit software, and what we're now doing is Qiskit quantum hardware. So totally new ecosystem in a sense. At the same time, those two ecosystems don't live in isolation. They're two ecosystems that do have to work in tight integration at some point. So what happens with Qiskit is that, Qiskit at the highest level, Terra abstracts completely the hardware, right? It's just gates X, Y, Z, whatever. As you move lower down the stack, you get to things like Qiskit Pulse, which actually talk about the Hamiltonian of the device. They need to know the parameters, like what is the qubit frequency, what is the qubit anchronicity, what is the qubit-qubit coupling. Those are things that you can simulate and run and use in Qiskit Pulse. Things you might need for optimal control, things that Mike is doing and so on. And so those are the kinds of things that Qiskit Metal can tell you in greater detail than anything else. They can report and tell you. So if you want, the picture doesn't really end here. There's another arrow that goes to Qiskit Pulse. We haven't yet made that connection, or like to Q-tip and things like that, but we would, I think that's on the roadmap to do in the next 3 months, is to connect the outputs of Qiskit Metal, which are the Hamiltonian and so forth, to Qiskit Pulse as the sort of next immediate thing. So thank you, that's a great question.
So I wanted to get back to the simulation part a little bit, the backend simulation. Is there sort of a recommended set of software suites that IBM sort of would recommend based on either their or the alpha cohorts experience? So if somebody just wanted to download those, or will there be sort of a community portal where you can kind of design your chip and go to this and try to simulate it, or whether one is on their own to simulate their chip once they end up designing it on Metal?
Yeah, thanks. That's a great question. So I think so in principle, Metal can work with anything because it's as long as you have an interface. In practice, personally, I've just used ANSYS since ANSYS since 2011 quite heavily. So that's the one I've tended to use, and I've got great results with it. Not saying that it's the best, or other softwares can't do it, or I think again, Keysight has some fantastic stuff. So actually, we're very excited to potentially do something with that. So those are new. There's also open source stuff, right? There's things like FastCap, FastHenry, or I'm forgetting all the names now, but there's a bunch of open source simulators. So we haven't yet had the time or chance to write renderers for those, and I'm not sure we necessarily will, but I think if those are things that you're using or interested in using, we would definitely love to help support and help work with you to create a connection with also other software. There is a lot to do, and it's a community project, so we can't ourselves do everything. It's more about helping others and enabling others to also build and grow and do that. So
Certainly.
it's hopefully that helps.
Yeah, thanks. No, the open source design is one thing, but open source simulation is almost lock and key with this thing, because a lot of people may not have access to commercial licenses to ANSYS or anything like that. So that might help.
I agree. Yeah, I think we should do it. Yeah, there's also Open Foam, I think it's called. There's another one, but yeah, that's a good one.
No problem. Thanks.
What about crosstalk kind of simulation is possible?
Oh, thank you.
Qubits are increasing. One more question, basically, how many qubits we can simulate? Like as the number of qubits are increasing, the crosstalk is an issue. So such a things would be possible in this?
Yes, perfect question. I think Metal gives you the ability to do general simulation. So impedance SCY. So for crosstalk, well, there's two types of crosstalk. There's classical quote unquote crosstalk and quantum quote unquote crosstalk. For classical crosstalk, like the one you just have between two wires because they're too close to each other, the sort of vanilla thing that is very complicated, but it's just classical. So I say just maybe that's undermining it. It's very important, and it's actually quite hard to figure out. But for things like that, yes, you can use this kind of SC matrix. Maybe Thomas will even talk about it next time. But basically, with Metal, you can define ports like drive port and yeah, just ports for simulation. So you can see if I put a voltage at this frequency at this power here, how much leaks through over here. So that's why it's very important to have these open short terminations. Dennis will at some point talk about how you can also put in ports here that can drive the system. So you can look at if I put a little signal here, how much leaks over to this part of the chip. So that's something that's built into Metal, and we haven't done much with it yet, but it's on the list, I guess, of things that folks can do and tell us how it works.
This is 2D, but actually once the number of qubits are becoming more, it will become a 3D kind of chip. So at what number of qubits basically that will turn to 3D? Any inputs?
Yeah, so well, the actual simulation is 3D, even though the layout is planar. But the simulation is fully 3D. It doesn't take approximation. This particular one here, HFSS, Maxwell's equations. There's no approximation. How much you can simulate kind of depends on how big of a computer can you buy or do you have. So the bigger RAM, the bigger thing you can simulate. So that's one of the main limitations there. The other one is that at the end of the day, you need, the chips are going to be complicated. So you're going to do sub-circuit analysis. You're going to need to rely on techniques like the one I just published on here with the team with this paper. This paper here, it doesn't try to simulate the full chip. It tries to simulate the chip by breaking it up into pieces. Like, take a sheet of paper and cut it up with scissor, understand each of the little pieces by itself and stitch them back together. That's what this does. So at the end of the day, I think, yeah, you don't have a way out of this. You have to use methods like this one.
Okay, thank you.
Yeah. Nile, do you have your hand up?
No, I'll just put it down. Thanks.
Great, thanks.
I have a quick question. Flux as a tunable parameter in Metal, or what do you think?
Oh, thank you, Wensen. Good to see you again. I think the question, you're kind of breaking up, but I think the question was about flux tunable qubits.
Yes. So is flux a tunable parameter in the Hamiltonian generated by metals at this point?
Oh, good question. Yeah, so let me go to that. It depends on which simulation you do. Like if you do the one thing you can just do manually is just change the let me try and find the right slide. Change the inductance. If you just have a flux, and a flux tunable Josephson junction, you just change the inductance. So if you change the inductance, it's the same thing as tuning the flux. In terms of the Hamiltonians that you put out, I think that's work currently that we're building up and doing. So I'm actually hoping we can maybe even leverage some things like SC qubits, if you're familiar with that have that already defined. So we'll sort of build out that interface from there. But right now, the thing you can immediately do is just change the inductance LJ and use that as your flux knob, essentially.
I see. Thank you. I'll try it out. Cool.
Yeah. Try it out and maybe Slack us if it doesn't, if it's not what you meant. Awesome. Any final questions? I see we're sort of over 10 minutes over the hour. Maybe I'll take any final questions. I know we've had quite a few already, and thanks to the team also for answering questions during the talk. All right.
Zlatko, there was a question and it was answered, but just this is all open source. Everybody who contributes, it stays open source.
Oh, yes.
You want to expand on that?
That's a really important question. Thank you, Priti. Yeah, that's an awesome question. Yeah, but that's maybe super critical. Actually, if I go to the documentation page, I think we have a nice note here. So this is totally open source. You can download it and have it, use it. There is no restrict, like if you create a device with Qiskit Metal, it's your device, it's your intellectual property. We don't take any right or own of that. You can see let's see, where's the documentation here? If you contribute code back to Qiskit Metal, then you sign something where it says that you're okay contributing the code, and you're not going to sue us, anything like that. But it is completely open source, and yeah, the license is a path, which is the most permissive open source license. It's not like GPL, which is far less permissive. So yeah, I think the short answer is it's open source, it's free in that sense. You can use it. Do cite the papers. I think we have a DOI for Metal, so if you do publish with it, I guess as an open source project, it benefits from you citing it. And hopefully that covers it. Good. I think with that, folks, it's been a real pleasure. Again, kudos and thanks to the team for also answering many of the questions during the chat. Thank you for your time tuning in today. Thanks for all the icons and emojis and making all the different time zones from 9 a.m. to 9 p.m. and beyond. And we will see you next Thursday with Dr. McConkey, Thomas McConkey, who will talk about how to actually do all of this with the code and do some awesome work. So thank you very much for your time today, and we'll see you next Thursday at noon Eastern Time.